Also thank the organizers for inviting me, and it's my great pleasure to be here. So today my talk is about the global dynamics of the heterogeneous Lotka-Volterra competition system. Spatial heterogeneity is a very common factor in the environment where the species lives in, and there are, so here is the motivation, like why I study spatial heterogeneity. So actually there are many remarkable phenomena that has been observed before my study. So first, the single species model. So it is observed by Professor Low, who is also here, in 2006, that even in a single species model, we found that spatially heterogeneous distribution of resources coupled with diffusion will always support a total population larger than the environment's total carrying capacity. And if we move on to the two-species competition-diffusion model, then as Professor Low introduced yesterday, we have the slower diffuser always previous phenomena. And also in the weak competition case, when spatial heterogeneity is incorporated into the model, we have the competition exclusion phenomena. And there are also many other works on this direction, just to name a few. So in the rest of my talk, I will first introduce these three phenomena in detail to illustrate the difference when spatial heterogeneity is incorporated into the model. So first, for the single species model. So let's first start with the simplest case, logistic equation. So here, A is a positive constant. It represents the carrying capacity or resources of the environment. And U is the density of the resources. So here we have already done a normalization or scaling. And if we assume that the species lives in a bounded smooth domain omega, and then we assume that the species move randomly with diffusion rate d, then we get the PDE model like this. And so here, we impose Neumann boundary condition on, which means that no individual crosses the boundary of the habitat. Then it is easy to know that the constant A is globally asymptotically stable for this homogeneous PDE. So in the rest of my talk, I will use GAS to represent globally asymptotically stable. Okay. So as I mentioned in the beginning, like usually due to the uneven distribution of food, water, or nutrient, the growth rate may depend on the location of the habitat X. So now I replace the constant A by a positive function mx, which is non-constant anymore. Then we get this function, this equation. And then it is proved in a series of papers by Contreras and Kostler that for any positive D, there exists a unique positive steady state, which we denoted as theta dm, which is globally asymptotically stable. So for later reference, I'm going to write down this equation satisfied by theta dm. So this is the equation satisfied by theta dm. And it is observed by Professor Low in 2006 that the integral of, the integral of theta dm is always positive, that is always greater than integral of m. So the left-hand side of this inequality represents the total population that can be supported by the environment. and the right-hand side represents the total resources of the environment. So it means that the total population is always greater than total carrying capacity, and it is actually very easy to prove this identity. So if we divide the equation of theta dm by theta dm itself and then integrate on omega, then we get the following. So by divergence theorem, we have d gradient theta dm square divided by theta dm square plus the integral of m minus the integral of theta dm equals 0. And because mx is non-constant, so theta dm, the solution is non-constant, so this term is always positive, which means that the integral of theta dm is always greater than the integral of m for any positive d. So this finishes the proof. And now if we plot the curve of the integral of theta dm against the diffusion d, we get this red curve. And by the previous inequality, we know that this red curve always lies above this horizontal curve, which is the integral of m. And due to the asymptotic properties of theta dm, that is when d goes to 0, theta dm approaches m, and when d goes to infinity, theta dm approaches m bar, this red curve approaches this horizontal line when d goes to 0 or infinity. So several questions can be asked in terms of this figure. For example, what is the maximum value of this integral theta dm, and where is this maximum assumed? So in general, this is still an open question for a general given mx. And but I am more interested in the following quantity, which I denoted as EM. And again, so what is EM? We take the integral of theta dm divided by the integral of m. So here the bar denotes the average, or here we can also understand as the integral of the function over omega. Then we know that EM is always greater than 1 for any long-constant mx. And we ask several questions. For example, is EM bounded above for all positive mx? And if so, what is the supermum? And what is the optimal distribution mx that achieves the supermum if it exists? So these questions will have profound impacts on competition system, as you will see later. So I'm going to write down the quantity EM. So for a given function mx, so EM is the quotient of theta dm, integral of theta dm divided by the integral of m, and then we take sup over the diffusion rate d. So this is EM, and it is always greater than 1. Okay, so this is the first example I give for the single species model. And the next example is about the two species Lotka-Volterra competition model. So again, I will start to introduce the ODE system. So U and V represents the population density of two competing species. So here A1 and A2, for the moment, they are positive constant, and it represents the carrying capacity for the species U and V, respectively. And the coefficients B1, it is a coefficient in front of U in the equation of U. And similarly, C2 is a coefficient in front of V in the equation of V. So they represent intraspecific competition or self-regulation coefficients. And the crossing term B2 and C1 in this system, they represents the interspecific competition. So in the following, I'm going to assume that both U and V live in a bounded smooth habitat omega, and they can move randomly. Then we obtain the following system. So here, D1 and D2 are the diffusion coefficients of the species U and V respectively. And I kind of change the letter A1 and A2 to M1 and M2. Also, I rescaled the intraspecific competition coefficients B1 and C2 in my previous slides to be 1. So only the two interspecific competition coefficients B and C remain in my equations. And this can always be done. Okay. So what can we say about this competition system when the environment is homogeneous? Actually, there are a lot of work has been done when M1 and M2 are constant. Then it is a classical homogeneous Lotka-Volterra system. And then I will always assume that BC is less than or equal to 1. And a lot of people have been working on the global dynamics for the homogeneous system. And let's not even read this theorem at all because it's very long. But I have a good picture to illustrate it. So here it is. And again, for later purpose, I'm going to put the picture on Blackboard. So this is the BC plane, and this is the curve, BC equals 1. So because at the moment I assume that both M1 and M2 are constant, so I have two threshold values. The first is M2 over M1 for the parameter B, and another threshold value is M1 over M2 for the parameter C. And the conclusion for the homogeneous Lotka-Volterra system is the following for its concerning its global dynamics. So if we pick a point C, for any point C bigger than or equal to M1 over M2, so namely in this region, then the global dynamics is the following. It's always U wipes out, V wipes out V, U. Namely 0 M2 is globally asymptotically stable. So here, 0 M2 is globally asymptotically stable. Symmetrically, when B is greater than or equal to M2 over M1, then the semi-trivial steady state M1, 0, is globally asymptotically stable. And in this rectangular region, we know it corresponds to the weak competition case, and there is a unique coexistent steady state, which is again globally asymptotically stable. And there's a very special point that is a degenerate case here. And then what we have is there exists a continuum of steady state collecting the two semi-trivial steady state. And this result is actually well known, but here I described this result in detail because later we will do a comparison for the case when when M1 and M2 are heterogeneous. So again, before we do that, let's mention some results which has been done before. So the first example is a slower diffuser always prevails, and this example has been showed in detail in Professor Low's talk yesterday. So I will just mention it briefly. So here I assume that, so here the species U and V, they are almost identical except for possibly their diffusion rate, D1, D2. And then it is proved in 1998 that whenever D1 is less than D2, namely U is a Schnorr diffuser, then all solutions converges to theta D1 M0. So here, theta D1 M0 is the semi-trivial steady state when we set V equals 0, right? And if we compare to the case when Mx is constant, then we know that it corresponds to this point where there is a continuum of steady state, namely U and V always coexist. So this is the difference when spatial heterogeneity is incorporated into the model. And as we know that Mx is non-constant is a crucial condition for this theorem to hold. And here I would like to mention an open problem, that is, when there are more than two species involved, it is still not known whether the slowest diffuser would prevail, although we highly believe so. So this is about the slower diffuser always prevails phenomena. And the next phenomenon is even striking. So let's assume that the competition ability for U and V are not identically 1. So we put B and C back. And let's choose a point, BC, that is less than 1, namely the weak competition case. And in the homogeneous case, we know that for the weak competition case, there exists a unique coexisting steady state that is globally asymptotically stable. However, in 2006, Professor Low proved that for some B less than 1, but greater than 1 over EM, where EM is defined here, and there exists some C sufficiently small such that theta D1 M0 is globally asymptotically stable for some properly chosen D1 and D2. So this means that even in the weak competition case, that is both B and C less than 1, we can find some coefficients, some diffusion rates D1 and D2 such that U can wipe out V. So coexistence is no longer possible even the competition is weak. And again, this is only possible when we incorporated spatial heterogeneity into the model. And later on, there are work done by Lam and Ni in 2012. So this is to me, this is a very important example that motivated me to study the effect of spatial heterogeneity in the competition or in the global dynamics of this system. So here is my goal in the rest of this talk. So I would like to clarify the combined effects of diffusion, D1, D2, spatial variation, which is M1 and M2, the resources function, and the competition ability, which is denoted by B and C, on the global dynamics of this system. And also I want to quantitatively measure how advantageous a spatially heterogeneous distribution of resources is. And finally, I would like to know if there is an optimal distribution of resources if all the previous questions can be resolved. And this seems to be too abstract as a question to deal with. So let me ask several specific questions. The first question is, in the slower diffuser always previous case, we know that U and the distribution of resources for U and V are the same. So let's assume that what if we assume that the spatial distribution of resources for U is long constant, that is Mx long constant, and the distribution of V is constant, which is defined as the average of Mx. So if we look at these two competing species, they have the identical competition abilities because all the coefficients here are 1, and they have the same amount of total resources. The only difference is that the distribution for U is heterogeneous and the distribution of resources for V is homogeneous. And the question is, which species will do better? Who will win? And you may think about this for a while, because this question will be answered in the end of my talk. Okay, so the purpose for this question is just to compare the spatial heterogeneity and homogeneity. And my next question is even more general. Let's assume that both species U and V has identical competition abilities, namely all coefficients here are 1. And also I assume that the total resources for both U and V are the same, namely the integral of M1 equals to the integral of M2. But now, both M1 and M2 are long constant, and they are different from each other. And again, the question is, which species will win? Who will do better? And this seems to be more complicated to answer compared to the previous question.
Are you using the same D1, D2 for this one?
No. They are arbitrary always. Okay. So, and the last question is, if we put the coefficients B and C back, namely they are not 1, then what is the effect of competition abilities on the global dynamics of the general Lotka-Volterra system? So in the following, I'm going to first answer question 3 and then go back to question 1 and question 2. So there any question? So, okay, so then let's first look at the global dynamics of the general Lotka-Volterra system. So this is the full system. The D1 and D2 are different, positive, and M1 and M2 are in general different, and we have BC. And the only condition I have is that BC is less than or equal to 1. And because this is a 2x2 competition system, so it is monotone. And so its global dynamics is in a large extent determined by the steady state and their stability properties. So due to this reason, I'm going to first study the linear stability of the two semi-trivial steady states. So I'm going to introduce this elliptic eigenvalue problem. So for any given D positive and a weight function Hx, I denote mu1 of dH to be the first eigenvalue of this problem. And then it is well known that the linear stability of the two semi-trivial steady states are actually determined by the sign of some eigenvalue problems. And actually, we do not need to memorize this at all. So, and the trivial steady state 0, 0 is always linearly unstable for any positive diffusion rates. So due to this reason, now we can study the stability of the two semi-trivial steady states in detail, and I'm going to show how we do this, how we define all those sets. So suppose M1x and M2x are given and BC are also given. Then if in the first quadrant of the D1, D2 plane, if we pick an arbitrary point, we want to ask ourselves, what is the linear stability of the two semi-trivial steady states? And based on its answer, we define all those sets. For example, the set sigma u means that the region where the first semi-trivial steady state, theta D1, M1, 0, is linearly stable. So this is the set sigma u. So u corresponds to the first component, right? And similarly, we can define sigma v. So sigma v is here. It's a set where the other semi-trivial steady state is linearly stable. So this is 0, theta d2, m2, linearly stable. And as I mentioned in the previous slides, the stability, all these stabilities can be determined by the sign of this scalar eigenvalue problem. And basically when it is positive, then we know that it is linearly stable, and when it is negative, it is linearly unstable. So what happens if it is 0? In that case, the linear stability is degenerate, and we call it sigma u0. And basically, sigma u0 is the boundary of the set sigma u. So this is the sigma u0. And similarly, sigma v0 means the set where the semi-trivial steady state 0, theta d2 m2, its linear stability is degenerate. So you can think of it as the boundary of sigma v. So what is sigma minus? The minus sign means that the principal eigenvalue, when we linearize both semi-trivial steady states, we get a negative sign. So it means that both semi-trivial steady states are linearly unstable. And it turns out that we have the following mutually disjoint decomposition of the first quadrant Q as following. So here's the theorem. Whenever the product of BC is less than or equal to 1, then Q, the first quadrant of this D1, D2 plane, can be exactly decomposed into 4 types. The set where sigma u, the set where theta d1 m1 0 is linearly stable together with its boundary. And the second component is the set where the other semi-trivial steady state 0, theta d2 m2 is linearly stable together with its boundary. And the third set is where both semi-trivial states are linearly unstable, which is called sigma minus. And there's one special set which I named as pi. What is pi? Pi means that it's the set of the point D1, D2 where both semi-trivial the linear stability of both semi-trivial steady states are degenerate. So we have to subtract this point from the first component, the second component, and single it out.
Two questions. So my first question is that it seems that this theorem mainly says that when BC is less or equal to 1, you cannot have the bistability case.
Yeah, exactly.
Then second question is, that's right? Okay. So the second question is that the last set, I think that's empty usually, right?
Well, it's actually most of the time it's empty, but in the slower diffuser case, that set is exactly the diagonal line. So the set pi, yeah. So it's the most degenerate case, and normally it won't happen. And also in my picture, it does not show. So if I want to get a point like this, I have to modify my set sigma v a little bit. So for example, if they touch like this, then this point might be my pi. And it could happen that there's only one single point in the D1, D2 plane. So yeah, as Professor Low asked before, so the important thing about this theorem is that you see, you cannot find a point D1, D2 in the first quadrant that both semi-trivial states are linearly stable. You cannot find such point. Namely, you cannot deduce from the linear stability of the two semi-trivial states that to construct a coexistence set that's linearly unstable. And this is due to the assumption that BC is less than or equal to 1. And why I make such a deep composition? Because here is the Lotka theorem, which completely clarifies the global dynamics of this system. Namely, in the first component of the decomposition, so where theta d1 m1 0 is linearly stable together with the boundary, actually it is globally asymptotically stable. And similarly, in the second component of the Q, where 0 theta d2 m2 is linearly stable together with the boundary points, actually it is globally asymptotically stable. And thirdly, in the point where both semi-trivial states are linearly unstable, that is sigma minus, from the monotone flow theory, we know that there exists a stable coexistence state, and it turns out to be unique and globally asymptotically stable. So that is the first three statements of my theorem. Basically, it says that linear stability implies global stability. And finally, in the most degenerate case where the special set pi, then we have a continuum of staticity which collects the two semi-trivial steady state, and it is a compact global attractor of our system. So this system completely determines the global dynamics of this system in the first quadrant of D1, D2 plane. So,
can you find the boundary?
The boundary of this set? Yeah, it is where the principal eigenvalue mu1 is 0. Almost, actually. But later on, I will show some example to know more about the shape for some specific system, because so far it's too general. Yeah, as it is too general and we don't know what this set, what those components looks like. So next, I'm going to vary B and C and to see how those sets change. And more importantly, I want to compare with the spatially homogeneous case to see the effect of spatial heterogeneity. And that is what I'm going to do next. Okay, so I'm going to draw a picture like this in the BC plane. So now I go back to the BC plane, okay? So this is the picture for the homogeneous case. Now, for the heterogeneous case, these two threshold values, m2 over m1 and m1 over m2, each splits into two numbers, and I denoted them as LU, SU. So they are here. So this is LU, this is SU. And similarly, the other threshold value m1 over m2 split into LV and SV. And here is my curve. Again, my curve BC equals 1. And what the important thing is that the product of LU times SV is bigger than 1, so it lies above this curve. And similarly, this point SU, LV, its product is bigger than 1, so it lies here. Now you can see that previously in the homogeneous case, the region below BC equals 1 decomposed into 3 parts. Here, here, here. And now how many parts do we have? We have 1, 2, 3, 5, 6, 7. And this component is too small. Let me make it larger. So this is my LU. This is my LV. So then, what is the global dynamics when we look at in the BC region? And here is the answer. So whenever C, the competition coefficient C, is bigger than SU, then V wipes out U. Namely, the semi-trivial static 0, theta D2M2 is globally asymptotically stable. So this is where 0, theta D2M2 is globally asymptotically stable. So if you compare these two graphs, you will see that this region corresponds to this region. Okay, and symmetrically, if B is greater than or equal to SU, then here we have U wipes out V. Namely, the semi-trivial static 0 D1M1, theta D1M1 0 is globally asymptotically stable. So this region corresponds to this region. And again, in the rectangular box around the origin, we have a unique coexistence steady state, which is globally asymptotically stable. And this I denote as sigma minus equals Q. It just means that if you pick any point BC here, and if B is less than LU, C is less than LV, and then if you look at the global dynamics of the system in D1, D2 plane, then for any point D1, D2, they always coexist. So somehow the graph is a little bit complicated. You have to first pick the point in the BC plane, and then you go back to the D1, D2 plane to see all the global dynamics. Okay. So this is how I made this graph. So now you can see that we have 1, 2, 3 regions blank to be filled. And here is the interest where all the interesting phenomena happens. Okay. So they are the following. So if B is between LU and SU, but C is less than LV, then what you can say is that sigma V0, and pi are empty. What does it mean? It means that in the D1, D2 plane, the V can never wipe out U, because the set 0, D2M2 is never globally asymptotically stable. On the other hand, there are some points D1, D2 such that sigma U is long empty. It means that U can drive V to extinction, but not the other way around. So this is the region where diffusion-driven exclusion could happen, right? And symmetrically, if we choose V, the value C between LV and SV, and B is less than LU, then we find that the set sigma V is long empty. And remember that the set sigma V means that where C0 theta D2M2 is linearly stable, and thus it is globally asymptotically stable. So if BC lies in this region, then V can drive out U to extinction, but not the other way around. And finally, if both B and C are larger than LU and LV respectively, then we have all kinds of complicated phenomena happen, depending on where your D1 and D2 lies. So either U can drive out V to extinction, that is sigma U is long empty, or V can drive out U to extinction, or they coexist if the value B and C lies in this region. Okay, So basically, all interesting thing happened in this three parts. And so I'm going to answer the following question. That is, how should we choose, if we were able to choose the distribution of resources M1 and M2, how should we choose it to make sure that one species has stronger competition ability? And here is one possible view to think about it. So recall that I have defined, LU and LV. They are here. So this is my LU, this is my LV. And they are defined as following. So it is the previous threshold value M2 over M1, but times a factor 1 over EM1. So as I mentioned at the very beginning that the EM1 is always greater than 1. So this is how we get ELU. And we have the following conclusion. So if somehow we can increase the value of EM1, then LU gets decreased. Okay. So what does it mean? It means that for some in the BC plane, okay, so let's remember one thing, that is, if EM1 is increased, then this will implies that LU will get decreased. Now, let's go back to the previous picture. Suppose I have a point, suppose my B is here. The competition ability of U over V is here. Now, if I modify my spatial distribution of M1 such that EM1 get increased, in that case, LU will decrease. Then what does it mean? It means that now I lies in this region. So if I choose my spatial distribution, if I can modify my spatial distribution, then the competition ability of U can get increased, because now U could drive out V to extinction for some appropriately chosen D1 and D2. That is one way to, so from my opinion, that's one way to enhance the competition ability for one species. I hope it's clear. So basically what I said is, if I decrease my LU, then previously the competition is maybe they just coexist, like here, but then it moves out to this region, then U could wipe out V for some D1 and D2. That is where diffusion-driven exclusion occurs. Okay. So then it comes naturally the following question. Because we want, so it seems that if the total resources of M1 and M2 are given, then somehow if I can find the supremum of EM and the distribution that corresponds, that attains this supremum, then the species adopt such resources, such distribution of resources will again the strongest competition ability in general. Okay, so however, this question, so far we were only able to answer this question in the 1D case when omega is an interval. And in the higher dimension case, we still don't know how to do this. Okay, so that's about the global dynamics of the general system. So let me move on to my first and second question. So let's review the question. So remember that when M1 is equivalent to M2, and when their competition ability are also the same, then we get the slower diffuser over the previous case. And we talked about this many times now. And now my second question is, what if they are still long constant? M1 and M2 are still long constant, but they are different. Okay, so I want to compare different spatially heterogeneous distribution of resources. And also I want to compare spatial heterogeneity and spatial homogeneity. That is, M1 is long constant, but M2 is constant. And in all those questions, both species U and V have identical competition ability and the same amount of total resources for comparison purposes. Okay, so I'm going to answer question 2 first, and there you can see how those sets sigma U, sigma V are studied in more detail. Okay, so first, let's assume that first I will answer question 2, that is M1 and M2 are different, but they are both long constant. Then in this case, here is the set sigma v. It's actually a set above this blue curve, which is a function of d1. Okay, and moreover, when d1 approaches 0 or infinity, this blue curve tends to infinity, just as I draw here. So this is the set sigma u, namely where if I pick a point d1, d2 here above this blue curve, then u wipes out v, or theta d1 m1 0 is globally asymptotically stable. So symmetrically, we can find the set sigma v, which lies above this blue curve. It is a function of d2, and again, as d2 approaches 0 or infinity, this blue curve tends to infinity, just as I draw here. And the interesting thing here is that the two regions, sigma u and sigma v, are disjoint and they never touch each other. So namely, their closure are again disjoint. So in this case, we couldn't find the point pi, where the most degenerate case happens. It won't happen for this particular system. And where is sigma minus? So sigma minus is the first quadrant of d1, d2 plane. Subtract the closure of sigma u, subtract the closure of sigma v, and due to the theorem, we know that for any point in this yellow region, there exists a unique coexisting steady state that is globally asymptotically stable. So now we get almost the picture of sigma u, sigma v, sigma minus, or almost everything. And actually, Professor Low asked me the question every time when he meet me. He said, like, what is the asymptotic profile when I choose point d1, d2 here in the yellow region, and when d1, d2 goes to infinity? And why this question is interesting? Because we know that if my diffusion d1, d2 lies in the region sigma u, we know that the globally asymptotically steady state is theta d1 m1 0. And if we move along the curve across this yellow region to the region sigma v, then the globally asymptotically steady state is 0, theta d2 m2. Then the natural question is how this profile changes if we move a point from here in a neighborhood of infinity to here. And I would like to emphasize again that because sigma u and sigma v, their closure are disjoint, and this blue curve tends to infinity, so there always exists some point d1, d2 go to infinity such that we have coexisting steady state. Okay, so to make my question clear, basically what we have is the following. So we know that sigma u, sigma v, they are disjoint. And here is the global asymptotically steady state. And if we move a curve, if we move d1, d2 along a curve like this, cross the region sigma minus, then the global asymptotic steady state becomes 0, theta d2 m2. And then we want to know how the profile changes, how the first component changes from theta d1 m1 to 0, and the second component changes from 0 to theta d2 m2 if we move along the diffusion curve like this. Okay, so, and before we answer this question, we need to obtain more detail the asymptotic profile of these curves, namely d2 star of d1 and the d1 star of d2, which defines sigma u and sigma v. So for this purpose, I'm going to define a quantity which is named Cm. So Cm is defined as following. So for any given resource function m, I'm going to solve the following problem, that is Laplacian rho m plus m bar, the average of m, times m minus m bar, subject to Neumann boundary condition. And moreover, I assume that the integral of rho m is 0. So I have a unique solution to this problem. Now, for the solution rho m, I take the L2 log of the gradient of rho m squared divided by the measure of the domain omega times m bar squared, and I define this quantity to be Cm, and it is always positive. And then, why I name it as Cm? Because, as you will see in later examples, Cm could be a measure of spatial concentration or variation. So, having defined Cm, let's look at the asymptotic profile of these two blue curves, which define sigma u and sigma v, respectively. And so, so if we look at the curve, the upper curve, d2 star of d1, then asymptotically this curve approaches a straight line with slope cm2 over cm1, d1 plus m1 plus some higher order terms as d1 goes to infinity. And what about the second curve, the lower curve d2 star of d1? Then as d1 or d2 goes to infinity, this curve, the asymptotics of this curve is again a straight line with the same slope cm2 over cm1 plus b1 minus b1 prime. So this curve, asymptotically, the lower curve d1 star of d2, you just shift down the previous line by distance b1 prime, and b1 prime is always positive. So this is how you get the asymptotics of these two curves. Now we can answer the question. So let's define a red straight line in between these two asymptotic straight lines. Remember that when s equals 0, then the red line is exactly the asymptotics of the upper blue curve from my previous theorem. And if s equals 0, we get exactly asymptotics of the lower blue curve. So now, all the straight lines in between can parameterized by the parameter s between 0 and 1. And here is the asymptotics of the unique steady state in this region when d1, d2 goes to infinity. That is, when d1, d2 goes to infinity, the unique coexistence steady state uv approaches 1 minus s times the total resources m1 times the total resources. And the second component v approaches s times the total resources. And this is not that surprising at all, because as d1 and d2 go to infinity, then the system is spatially averaged. So if you add them together, if you add u and v together, there has to be the total number of resources, which is m1, which is the integral of m1 or the integral of m2, but they are the same, right?
But the interesting thing is that the s really depends on how d1, d2 ratio in some way, right? Because that's not easy to see. When d1, d2 go to infinity, it's easy to see coexistence will approach steady state, constant steady state.
Yeah.
But the s is not easy to find out.
Yeah. So basically, you have to go to the second order expansion of all these the profile of u and v, and so basically now we can see that it moves almost continuously from this region to this region in a neighborhood of infinity.
So my point is that maybe you didn't catch my point. So if I ask you, you let d1, d2 go to infinity in some ratio, then s depends on that ratio, right? And you still catch that ratio, right? Well, we can talk about that later. What I said, you proved more than what's here.
Oh, okay. Sorry. And so now so how many time do I have?
You have 12 minutes.
Oh, okay, good. So let me give some more specific example to illustrate the importance of this ratio cm1 over cm2, because you see this ratio kind of almost divide the like how many portions does sigma u has and how many portions sigma v has in the first quadrant of the D1, D2 plane. And so the first example I'm going to have is, let's assume M1 equals 1 plus alpha times gx, and M2 equals 1 plus beta times gx. And here I assume that the integral of g is 0, so that you see M1 and M2 has the same amount, same integral, right? So the only difference is, and here in particular I assume that U and V has the same diffusion coefficients. So I choose the same one, D. And so basically U and V, the profile of U and V are the same. It's just U has a bigger amplitude in its oscillation. And the answer is the following. So we have Cm2 over Cm1, this ratio, equals beta over alpha squared, which is less 1. Because I have chosen alpha is bigger than beta, bigger than 0. And what does it mean? It means that if we draw the diagonal line in the D1, D2 plane, because this slope, Cm2 over Cm1, is always less than 1, it means that for all d sufficiently large, U will wipes out V, because then this diagonal line lies in the region sigma U. That is where theta D1 M10 is globally asymptotically stable. And on the other hand, if D is sufficiently small, then they coexist. Okay. So it seems that, well, I have to mention that for the intermediate D value D, I don't know. So either could happen. Okay. So it seems that in this case, the larger concentration case is more favorable for the competition. But what about the oscillations? And for the oscillations case, I have the following example. So again, let's assume that the total resources for U and V are normalized to be 1. And then the profile for U is 1 plus cosine K1 pi x. And for V is 1 plus cosine K2 pi x. So basically you have the following picture. So suppose we are in the interval 0, 1. And here is 1. Then the distribution of resources for U is 1 plus cosine K1x. So suppose K1 equals to 1. And then maybe for V, I choose to be like this. You get more oscillations. So this is M1. And when you have more oscillation, you get M2x. And then we want to compare the competition between U and V. And the answer is following. So for positive integers K1 less than K2, we have Cm2 over Cm1. The ratio of the symptotic line of these curves is again less than 1. It means that if we draw the diagonal line in this D1, D2 plane, it means that for all d sufficiently large, U will wipes out V, because now this red line eventually will lies entirely in sigma U. That is where sigma theta D1 M1 0 is globally asymptotically stable. So it means that again for D large, U wipes out V, and for D sufficiently small, they coexist. And for intermediate D, again, the answer is not clear. So either case could happen. So this is all about my second question, that is when both species has different heterogeneous distribution of resources. And you can see that somehow the competition between them has some symmetry, but also has some asymmetry due to this slope. Slope is not necessarily 1. Okay. And finally, I'm going to answer the question that is when U has spatially heterogeneous distribution, but V has spatially homogeneous distribution, what happened? And I want to draw your attention that this is not a special case of the previous situation, as you can see here. So basically, we can find a curve, which is a blue curve here, divide the first quadrant of D1, D2 plane into two parts. Above this curve, we have theta D1 M1 0 is globally asymptotically stable. That is, U wipes out V. So which means that whenever you increase your diffusion rate to D1 or D2 sufficiently large, you will always win the game. This is quite different from the slower diffuser always previous case. And in the yellow region, that is below this blue curve, both semi-trivial statistics are linearly unstable. Namely, we always have a coexist steady state that is unique and globally asymptotically stable. So in general, we can see that U has some U is more superior than the species V during the competition. And so that is what we have for general M. If we assume that if M satisfies an extra condition, that is the infimum of rho M plus Cm is positive. Remember that what is rho M? Rho M is a unique solution to the following problem. So Laplacian rho M plus M bar times M minus M bar equals 0, subject to Riemann boundary condition and the integral constraint rho M equals 0. So this is how we define rho M in terms of M. And rho M changes sign, right? Because its integral is 0. So we take this infimum plus the positive constant, the positive value Cm. If this is positive, then we get even more. That's the following. So actually this blue curve will hit the D1 axis at some finite value and terminate there. And now above this curve, again, we have theta D1 M1 0, globally asymptotic stable. Namely that if D1 is larger than this threshold value here, no matter how you choose D2, U will always wipes out V. Okay. So more detailed asymptotics can also be obtained for these curves in either case, but for the time reason, I'm not going to talk about here. And so let's summarize what we have for this special situation, that is both U and V has identical competition abilities and the total resources are the same. So at the very beginning, it is proved, like in 1998, that we have slower diffuser always previous when M1 is equivalent to M2. And now if we choose them to be different, but still with the same total amount of resources, then somehow this yellow diagonal line gets flattened to this sigma minus, this yellow region. And again, the competition between U and V has some symmetries, but not exactly, because the slope of this asymptotics of those two blue curves. And finally, when U has spatially heterogeneous distribution of resources, but V, the distribution of V is constant, then we get this picture. So U can wipe out V in a large region of the D1, D2 plane, but V can never wipe out U. Okay, so that is the global dynamics for all the three cases. And so here is a summary. So diffusion-driven exclusion is possible only when spatial heterogeneity is incorporated into the model if we compare these two pictures. Right? And also, the strength of competition ability must lie above a threshold value. That is these three regions. Here, here, and here. So these are where more complicated situations or phenomena could happen, depending on the specific choice of D1 and D2. And our conclusion is that the larger EM, the more advantageous for the competition of that species. And finally, we find that heterogeneous distribution MX seems to be more superior to the homogeneous distributions of resources. And I would like to thank you for your attention.